So I've been having a bit of an existential crisis with my computer lately.
Oh, really? How so?
Yeah, it's like I'll ask
What?
ChatGPT something incredibly complex, something you'd think requires actual human-level deduction, and it just nails it.
Right.
But then 10 minutes later, I give it a simple math riddle, and it falls on its face so hard it's embarrassing. It really feels like these models are either secret geniuses or just, really confident idiots.
That is the ultimate paradox of the large language model. I mean, we're dealing with systems that have basically read the entire internet, right? But they sometimes struggle with things a 10-year-old could do in their sleep.
Exactly. And that brings us to the paper we're diving into today. It's by Jason Wei and the Brain team at Google Research. The title is Chain of Thought Prompting Elicits Reasoning in Large Language Models.
A very academic title for a very wild concept.
It is. And honestly, when I first saw the title, I thought, oh, great, another paper on prompt engineering. Just tell me the magic words to type to get what I want.
Right, like a cheat code.
Yeah. But this feels, I don't know, it feels different. It feels less like a hack and more like a fundamental discovery about how these things actually process information.
It absolutely is different. This paper is sort of a watershed moment in the field because, it challenges the big assumption that the only way to make AI smarter is just to make it bigger.
Right.
The Google team essentially asked, what if the model already has the reasoning ability, but we're just not giving it the space to use it?
The space to use it. That's a really interesting way to put it, because for the longest time, the standard approach has just been scaling, right?
Oh, 100%.
You just feed the beast more data, give it more parameters, and hope intelligence magically emerges.
Precisely. And for a long time, that strategy worked beautifully. You scale up and you get better grammar, you get better fluency, better fact retrieval. That's your system one thinking.
Like Daniel Kahneman's System 1 Fast, intuitive, automatic.
Exactly. But scaling was hitting a massive brick wall with system 2 tasks.
So the slow, deliberate, logical thinking.
Right. Things like arithmetic, common sense reasoning, symbolic logic. You can make a model 10 times bigger, and it might still totally fail at a multi-step math word problem because it tries to answer intuitively using that system 1 instead of methodically.
So to solve this, the Google team proposes this chain of thought method. And on the surface, it looks, well, ridiculously simple.
It really does.
Instead of just asking a question and expecting an immediate answer, you feed the model a few examples where you actually show the work.
You show the reasoning path, yeah. Just like on the math teacher telling a student, don't just write down the final number, show your work.
Right, and there's this classic example in the paper, the tennis ball example.
Ah, yes, the famous Roger.
Yeah, Roger. So if you're doing standard prompting, you just ask. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many does he have now?
And if you just ask that, the model, even a massive one, usually just guesses.
It just sees the numbers 5, 2, and 3, and it's like, 11, or maybe 27.
Or 8. It's essentially just pattern matching against similar sentences it's seen on the internet. It's trying to jump straight from the question to the answer in one giant leap. It's doing mental math without the mental part.
But with chain of thought prompting, the structure changes. You provide an example that says, Roger started with 5 balls. 2 cans of 3 tennis balls each is 6 tennis balls. 5 plus 6 is 11. The answer is 11.
Right. The prompt is a triple: input, chain of thought, and then output. You force it to decompose the problem into intermediate steps.
And this is where I think we need to get a little technical for a second, because reading this, the aha moment for me was realizing this isn't just about teaching the model good habits. It's literally changing how the model allocates compute, right?
Yes. Think about how a large language model works. It generates one token, which is basically a word or part of a word at a time.
Okay.
And each token takes a certain fixed amount of processing power to generate. If I ask you a really hard math problem and force you to blurt out the answer immediately, you have to do all that complex computation in your head instantly.
Which usually leads to me panicking and saying a random number.
Exactly. But if I let you write it down on a scratch pad, you are spreading that computation out over time.
So for an LLM?
For an LLM, the output is its scratch pad. It doesn't have an internal working memory where it can silently think to itself before it speaks. If it doesn't generate a token, it hasn't thought about it.
That is wild. So by forcing it to generate the sentence, 2 cans of 3 balls is 6, we are literally buying its CPU cycles to process those intermediate steps.
You got it. You are expanding the computational window for that specific problem. You're taking a deep, complex calculation and flattening it into a series of shallower, sequential calculations.
It aligns the model's linear token generation with the linear nature of human logic.
That's why chain of thought is so powerful.
Okay, but hang on. If this is really just about buying time and showing steps, why didn't we figure this out back with GPT-2 or the earlier models? Why is this suddenly a new discovery?
Well, that is the fascinating mystery the researchers ran into. They actually tried this technique on smaller models. And by small, I mean still relatively huge models with, say, 8 billion parameters.
And what happened?
It was a disaster. It didn't help at all. In fact, it often hurt their performance.
Wait, showing the work made the AI dumber.
It made them confused. The smaller models just aren't capable of maintaining a coherent logical chain. They would try to mimic the style of reasoning. They'd use words like therefore and since, but the actual logic was just totally hallucinated.
Oh, so they'd say things like, Roger has 5 balls, he bought 2 cans, so he has 5 minus 2.
Fluent, but totally illogical. They were just cargo culting the reasoning format.
Wow, so at what point does it actually start working?
It's what the researchers call an emergent ability. It barely registers as helpful until you hit a very specific, massive threshold of scale, somewhere around 100 billion parameters.
Okay.
Once you hit that scale, the performance graph just hockey sticks. It spikes straight upwards.
That's almost unnerving. It implies there's a critical mass of complexity you have to reach before logic just sort of happens.
It suggests that reasoning isn't a feature you program in. It's a side effect of scale. When they tested this on their absolute monster model, PM034B, the results were just staggering.
They used the GSMAK benchmark for that, right? The grade school math word problems.
Yes, and those are deceptively hard for computers. With standard prompting, that massive PaLM model only got about 17.9% accuracy. It was failing the vast majority of the time.
But then they switched to chain of thought prompting.
And it jumped to 56.9%.
That is not a marginal gain, going from 17 to nearly 57%. I mean, for a computer benchmark, that's huge.
It actually surpassed a GPT-3 model that had been specifically fine-tuned with a verifier just to do math. And remember, PaLM wasn't fine-tuned for this. It's just a general model that was basically asked nicely to think step by step.
It really highlights that standard prompting was only showing us the lower bound of what these models were capable of. So we have this simple method that unlocks latent intelligence in huge models. Let's look at where this applies, because the deep dive shows it's not just about tennis balls. The paper breaks it down into 3 main domains: arithmetic, common sense, and symbolic reasoning.
Arithmetic we've kind of covered. It allows the model to act as a translator, turning a messy word story into a clean math equation, like the cafeteria apples example.
Oh, right. The cafeteria had 23 apples. They used 20 for lunch and bought 6 more. Chain of thought lets it do 23 minus 20 is 3, before adding the 6 to get 9.
Right. And actually, for really hard math problems, the researchers found that if they added an external calculator like a Python program to the chain of thought, the accuracy boosted even further.
Because it offloads the actual arithmetic and just handles the logic. That's smart. But I think the common sense reasoning domain is my favorite, because this is the stuff that always trips up AI. It's the implicit knowledge of how the physical world works.
They use a data set for this called strategy QA. The questions are things like, would a pear sink in water?
Which requires knowing some physics, but also just knowing what a pair is.
A standard model might just guess yes or no based on random word associations. But with chain of thought, the model output this exact rationale. The density of a pear is about 0.6 grams per cubic centimeter, which is less than water. Thus, a pear would float. So the answer is no.
It actually derived the answer. It didn't just retrieve a memorized fact about pears and water.
It connected 2 completely disparate facts to form a logical conclusion. That is the definition of reasoning.
There was another one in the paper about sports that I found hilarious. The prompt was, João Moutinho caught the screen pass in the NFC championship. Plausible or not?
To a layman, that sounds totally fine. But to a sports fan, it's complete nonsense.
Right. And the model reasoned it out perfectly. It said João Moutinho is a soccer player. The NFC championship is American football. Soccer players don't play in the NFC, so not plausible.
That's the kind of context switching that usually breaks these systems. It has to identify the person, identify the event, and explicitly state that the 2 sets don't overlap. Oh, and it can even do date understanding.
Like what?
Like if a prompt has a clue about a concert being delayed and asks what the date was 10 days ago, the model can calculate the dates chronologically in its chain of thought.
That's incredible.
Right.
And then the third domain is symbolic reasoning. This is the really abstract stuff. Things like the last letter concatenation task,
Right, where you ask it to take the last letters of Amy Brown and put them together to get in.
which sounds totally trivial to a human.
But remember, large language models don't see letters. They see tokens. Amy is one token. Brown is one token. Asking an LLM to find the last letter is like asking you to find the last atom in a brick. You have to break the brick apart first.
So chain of thought forces it to say, the last letter of Amy is Y, the last letter of Brown is N.
It forces the decomposition, and they found something really cool in this domain called length generalization.
I wanted to ask about that.
Yeah, if you show the model an example of someone tracking the state of a coin flip, say, flipping it twice, and then you give it a problem where the coin is flipped 4 times.
It can still solve it, even though it's longer than the example.
Exactly. It learns the algorithm, the state tracking. It learns to keep a running tally of heads, now tails, now heads again.
Okay, this is all incredibly impressive, but I want to push back on this a bit.
Yeah.
Because I can hear the skeptics, and frankly, I'm usually one of them, listening to this and thinking, is it really reasoning? Or did we just figure out a better way to trick the stochastic parrot?
And the researchers absolutely asked that same question, which is why this paper is so scientifically rigorous. They didn't just show that it worked, they ran what are called ablation studies.
Basically trying to break their own method to see exactly why it was working.
They wanted to isolate the variable. Was it the math? Was it the natural language? Was it just the extra compute time?
Right. So first they tested the equation-only hypothesis, the idea that maybe the model doesn't need the whole story. What if we just prompt it to output 5 plus 6 equals 11?
And it failed. On the easy problems, it helped a little, but on the hard word problems, the GSM-8K accuracy dropped significantly.
So the words matter.
The semantics are crucial. The model needs those natural language words to translate the messy, real-world scenario into a clean math problem. If you force it to go straight to math, it loses the nuance.
Okay, so what about the thinking time theory? You said generating tokens buys compute. So what if we just tell the model to print a bunch of ... dots before the answer? Just generate empty tokens to spin the CPU.
The variable compute test. Yes, they literally had it output dots to simulate processing time before giving the answer.
And did it work?
Nope, flatlined.
Why not? If tokens equal compute, why don't empty tokens equal empty compute?
Because the compute needs to be directed. It's not just about spinning the wheels, it's about moving the car forward. The model needs to be generating content that actually narrows down the search space for the next token. Dots don't provide any logical scaffolding.
That makes a lot of sense. It's like me staring blankly at a wall for 10 minutes versus writing out a pros and cons list. One is actually thinking, the other is just daydreaming.
Exactly. And then they tried one last variation. Reasoning after answer. What if we let the model give the final answer first and then ask it to explain itself?
The answer is 11 because, which honestly is how most humans argue on the internet. State the opinion, then scramble to find the facts.
And just like in internet arguments, it doesn't lead to the truth. It failed. The accuracy didn't improve over the baseline at all.
Wow.
This proves that the reasoning isn't just window dressing, it is functional. The logic must precede the prediction to guide it. If you answer first, you've already collapsed the probability wave. You're just post-rationalizing.
That is a fascinating distinction. The logic has to be the engine, not the exhaust. And they also tested robustness, right? Like, did it matter who wrote the prompts?
They tested prompts written by different annotators and even a super concise style. And while there was some minor variance, chain of thought consistently outperformed standard prompting no matter who wrote the example.
But there was always a but with AI. This isn't a magic bullet. We can't just slap, let's think step by step on everything and call it a day. What are the limitations they found?
The biggest one is the black box issue, combined with hallucinations. We call it faithful reasoning.
Faithful to what?
Faithful to the truth. The model can generate a chain of thought that looks perfectly logical, follows all the rules of syntax, but is based on a complete hallucination.
Like the classic bats or birds syllogism.
Exactly. Bats are birds. Birds lay eggs, therefore bats lay eggs. The logic itself is sound. A implies B, B implies C. But the premise is totally false. The model can hallucinate a fact in step 1 and then logically deduce a perfectly wrong answer from it.
And because the explanation looks so structured and logical, we as users are way more likely to trust it.
That is the real danger. With a standard model, it just gives you a wrong answer and you might spot it. A chain of thought model gives you a wrong answer wrapped in a highly convincing 3-paragraph essay explaining exactly why it's right.
So it just becomes a much more persuasive liar.
In their error analysis of the Palm 62B model, they found cases where the model fundamentally misunderstood the semantics of the question. Other times, it did mostly right work, but just skipped one vital logical link.
Like getting the right math answer by making two mistakes that happen to cancel each other out.
Exactly. So while accuracy goes way up, the interpretability is still a bit of a mirage. We can see the steps, sure, but we don't actually know if those steps on why the model picked the answer or if it's just mimicking how a human would explain it.
So, stepping back, where does this leave us? Let's recap for everyone listening. Chain of thought prompting is this remarkably simple technique, just providing examples of step-by-step reasoning that unlocks massive emergent intelligence in models over 100 billion parameters.
Right. It allows them to tackle math, common sense, and symbolic tasks just by decomposing them, basically thinking out loud.
The big takeaway for me is that it proves we haven't even hit the ceiling of what current AI models can do. We just need to learn how to ask them the right way. It shifts the burden.
We've been treating these models like search engines, input, output, but they are inference engines. We were demanding the destination without letting them plan the route.
That is perfectly said. But I want to leave everyone with a final, slightly provocative thought that the authors touch on, and it's probably going to keep me up tonight.
Uh-oh.
We've been debating this whole time whether this is real reasoning or just an AI mimicking the structure of reasoning. But if a machine can break down a complex problem, apply sequential logic, error check its own state, and arrive at a novel, correct solution, at what point does the distinction stop mattering?
That is the question. If the final result is indistinguishable from thought, maybe the process is too.
If it walks like a duck and solves differential equations like a duck. You know where I'm going. Well, that wraps up today's deep dive. Thanks for exploring this with us.
Oh, it was a pleasure.
And to everyone listening, we'll catch you on the next one.